We are now going to look at Euclid's algorithm. It is an algorithm for finding GCD. I think this is one of the most amazing algorithms that exist in mathematics. To give you a sense of how old this is, I believe this appears in Euclid's book, which was written in 300 BC. So it predates all of, it's like one of the first things ever written about mathematics. And it's really simple, yet it like shows that in math, what you really need is to truly understand an object. And then by piecing very simple pieces together, you can create something really amazing and non-intuitive. And here's why it's non-intuitive. So recall that if you have M and N whose prime decompositions are given as follows, where M is a product of primes powers and N is a product of prime powers, then their GCD is simply take the prime powers, but take the minimum of both the powers. Okay, so it's the largest number that divides both M and N, and you can find it using the prime decomposition. Now, how hard is it to find GCD? When I ask this question, how hard something is, of course, for small numbers, you can just do it by hand. Like if I tell you find the prime decomposition of 14, you know it's 2 times 7. But the real question, the question that when such a question is asked, what you're really asking is, what if your number has 1,000,000 digits? How hard would it be to find GCD of numbers with millions or billions of digits? And that's not something that unusual. All your passwords are protected using some crypto system, and those crypto systems regularly use prime numbers, which are thousands of digits, if not millions. Okay, so it's very, very important to be able to answer questions for large numbers. So the first question then you might ask is, how hard is it to determine if a number is prime or not? And this is a hard but doable question. It was very recently, not very recently, it was recently proven that this is something called polynomial time. So which means that it's possible that in the future we will have very good algorithms to do this. Right now it's difficult, but it's doable. Then how hard it is to compute prime factorization of numbers. This is impossible. It takes exponential time, which means that if I give you a number with 1,000,000 digits, most supercomputers will not be able to find its prime factorization. And if you can't even find prime factorization, then you might ask, well, then finding GCD is a hopeless endeavor. But it turns out, no, finding GCD is actually very easy. It's linear in the number of inputs. So all, or not all, but at least most crypto systems use some form of this algorithm in their background. And this is Euclid's algorithm. So it bypasses the step of finding prime factorization and instead gives you a way to compute GCD just by doing some addition and subtraction, just addition, multiplication, subtraction, so basic operations. And it's completely, it's algorithmic. So it's a process that you can code, and then it will give you the GCD. It'll just output the GCD right away. And that's the amazing thing. I guess Euclid understood GCD so well, and he understood numbers so well, that he realized that it's not necessary to do prime factorization. You can bypass it and come up with this very beautiful algorithm that gives you the answer very fast. Okay, so that's the introduction, and now let's jump into Euclid's algorithm. So Euclid's algorithm, its goal is to find GCD of two numbers where M and N are positive integers. We'll stick to positive integers. And let's assume, without loss of generality, let's assume that M is bigger than N. Okay, then main idea of Euclid's algorithm is the following, that GCD of Mn, actually there are two steps, GCD of Mn is the same as GCD of N and M mod N. The proof of this is in the book. like already, I think it's going to take a while to go through Euclid's algorithm. So I don't want to make this video too long, so I'll skip the proof. But the proof is not difficult. If you understand GCDs well, you can prove this by yourself. It's a direct proof. You just have to expand out what GCD means and complete the proof. Okay, so we'll assume this, that GCD of two numbers is the same as taking the smaller number and then taking the remainder. Recall that this is the m mod n is the remainder when m is divided by n. Or the second observation is that m is bigger than n and n is bigger than m mod n. Recall that we always want our remainders to be less than the divisor that we're dividing by. But now look at what has happened. If I start with m and n, then I know that their GCD is the same as GCD of n and m mod n. But now n and m mod n are strictly less than the original numbers that I started with. So I reduce the problem to finding GCD of smaller numbers. And then I can do that again, and then I can do that again, and I can keep on doing that until the numbers are so small that I know their GCD. Essentially, I want one number to divide another. And once I reach that, I know their GCD, which is the smaller number. And that's it. That's the insight due to Euclid. And using this, you can find GCDs of numbers really, really quickly. So let's do some examples to make this clear. Let's say my question is find GCD of, let's do 82 and 26. These are small enough numbers that you can just do this by hand, but we want to do this using Euclid's algorithm. I'm finding GCD of 82 and 26. So first thing I need to do is I need to find the remainder when 82 is divided by 26. So I'll do a long division. 26 times, let's go 4. If I do 4, it's too big. Let's do 3. 3 times 26 is 8, 1, 7. Let's subtract, and I get 4. 4 is less than 26, so we are good. So what I can say is that 4 is equal to 82 mod 26. So that's the first step. Now I'll change my numbers to 26 and 4. Why 26 and 4? 26 was smaller of the two numbers I started with, so I'll keep that. And then 4 is the remainder that I found. So that becomes my new number. Okay, now let's, I need to again find the remainder when 26 is divided by 4. So that is 6. And here's my new remainder. So I will get 2 is equal to 26 mod 4. And now my new numbers are the smaller of the older numbers, which was 4, and then the new remainder that I found, which is 2. And because 2 divides 4, GCD of 2 and 4 is 2. And so GCD of 82 and 26 is the same as GCD of 26 and 4, which is the same as GCD of 4 and 2, which then equals 2. So I found the GCD of 82 and 26 to be equal to 2 without having to factorize either 82 or 26. So that's how you use Euclid's algorithm. You successively find the remainders, and then you keep throwing out the larger number. And these numbers get small really, really fast. Like, that's the amazing thing about Euclid's algorithm. You can do a runtime analysis and show that this is very, very fast. Now we'll take this to the next level and talk about extended Euclid's algorithm. So Euclid's algorithm lets us find the GCD of two numbers, but actually it does something more. And to see this, before I tell you what extended Euclid algorithm is doing, notice what has happened here. I kept the remainders, and I just use the remainders to find the final GCD, but I also have the quotients. Like, I also have the number 3 and number 6 which I'd completely discarded while I was doing Euclid's algorithm. And it turns out these numbers contain information that can be used to answer further questions. And that's what extended Euclid's algorithm is about. But before we get to the algorithm, I need to tell you a theorem. So let m and n be positive integers. And let D be their GCD. Then it turns out that there exists there exist integers x and y. X and y can be negative such that D is equal to m times x plus n times y. That is, I can write the GCD as linear combination of the two numbers where all the numbers involved are integers. This is highly non-trivial. And the reason the proof is non-trivial is because we are looking for integer solutions. This is very important, we're looking for integers. If you just said there exist real numbers, then this is a trivial, then there are infinitely many solutions. In fact, even here, there are infinitely many solutions. But finding real solutions is a trivial problem. Finding integer solutions is highly non-trivial. Okay, but Euclid's algorithm just gives these numbers right away. So you can think of Euclid's algorithm as a way of proving this theorem, although we won't go into the details of the proof. Okay, and that's what extended Euclid's algorithm is. And I'll explain how to do this using Euclid's algorithm. Before we jump into the algorithm, there's one thing that one equation that we'll use repeatedly. So let me write that down here explicitly. So suppose m mod n is R and m div n is D, then you know that we can write m as n times D plus R. That's what it means to have a remainder and a quotient. And then I can further write R as m minus n times D. Okay, so I can write the remainder as the bigger number minus the smaller number times the quotient. And this is the step that we are going to use repeatedly in addition to Euclid's algorithm, and use this to solve the above problem. Okay, so it's all abstract route, but I'll do an example where it'll become clearer. So here we go. We'll stick to the same numbers, and I'll say find integers, very important, x and y, such that 2 is equal to 82 times x plus 26 times y. And why 2 on the left? Because recall that we showed earlier that 2 was the GCD of 82 and 26. The first thing we need to do is to run the standard Euclid's algorithm. Now, because I already ran it above, let me copy it. So this was the Euclid's algorithm we ran. We first started with 82 and 26. These were the two numbers that are given to me. Then I found that 4 was the remainder. Then I replaced 82 and 26 with, 82 and 26 with 26 and 4. And those became my two numbers. And then I found the remainder again, and the remainder turned out to be 2. Then 4 and 2 became my new numbers. And my algorithm stopped at that point. But now I need to find something more than the GCD. So here's how I'll do it. First, I'll systematically write each of these blocks using the equation that we just did above, that R is equal to m minus n times D. Okay, so first thing is to find those equations in each of these things. So first thing I'll get is, because 4 is my remainder, I'll get 4 is equal to 82 minus 26 times 3. And where is the 3 coming from? 3 is the quotient. All right, then I'll do the same thing for the next step, and I will get 2 is equal to 26 minus 4 times the quotient. In this case, that is 6. And because 2 was the GCD, I'll just stop here. I don't need to go further. So I need to reach my GCD. Okay, so now I have found a way to write 2 as 26 minus 4 times 6, but that's not what we're wanting. We want something in terms of 82. So now what I'm going to do is I'm going to start with the bottommost equation, and I'll notice that in this equation there's a 4, and in the equation above there is also a 4. So there's a 4 here, and there is a 4 here. So what I'll do is I'll start with the bottommost equation and replace that 4 with the above 4. So I'll do this replacement. Okay, and if there was one more equation above, then I would have done the same thing again. And I'll keep on doing this. And you'll see that magically I'll get the numbers x and y out of this process. So let's start. I'll start with the bottommost equation. This is 26 minus 4 times 6. Now I'll replace this 4 with everything in the above equation. So this is 26 minus 4 is 82 minus 26 times 3, and then 6. And now I will just expand everything out. And now I see that there's 26 in the first term and 26 in the third term, so I can combine them together. So I'll get 26 times 19 minus 82 times 6. And then I'll just rewrite them, rearrange the terms slightly, so that I will get 82 times minus 6 plus 26 times 19. And if you look at what this equation is saying, it's saying exactly what I wanted in the question, that I can write 2 as 82 times an integer plus 26 times an integer. And so my answer is x is equal to minus 6 and y is equal to 19. Just to show you the original question, we had fine integers x and y such that 2 is equal to 82 times x plus 26 times y. And that's exactly what I've done here. And now let's just verify. It's always a good thing to verify, although this step is optional. You don't have to do this step when you yourself do the algorithm, but it's always a good thing to do. So let's see what 82 times 6 is. So 82 to 6 times 2 is 12. 1 times 8 is 48. So I get 49. And you can see that 26 times 19 is 494 and 82 times 6 is 492, and their difference is exactly 2. And now one last thing about the extended Euclid's algorithm, it does even more. So we found integers x and y such that notice that in Z mod n is equal to 0. Why? Because n mod n is 0. That is, if you were to divide n by itself, then the remainder would be 0 because n completely divides itself. Then in Z mod n, the above equation becomes d is equal to m times x plus 0 times y, and which then is just m times x. So what I'm saying is that in Z mod n, using Euclid's algorithm, we can find an integer x such that GCD of mn is m times x. Now we'll specialize a little. Now further suppose GCD of m comma n is 1. Of course, this is not true for the example we did above, but like you can have m and n are like 3 and 5, in which case this is true. So if you have this extra special condition, then the above equation becomes 1 is equal to m times x. in Z mod D, in Z mod N. So what we are saying is that if I give you two numbers m and n such that their GCD is 1, then I can use Euclid's algorithm to find an x such that m times x is 1 in Z mod n. But what is this saying? This is simply saying that x is equal to m inverse. And so I can use Euclid's algorithm to find the multiplicative inverse of m in Z mod n. And this is crucial in the RSA algorithm. The RSA algorithm relies heavily on, you have something called a public key, and then you have to invert it in something called a private key. Not exactly, but it uses this fact heavily, that you can very efficiently find the multiplicative inverse of a number in Z mod n using Euclid's algorithm. And we will see how that's done in practice in a later video.